So, our sun will die as a white dwarf. All low-mass stars will eventually die that way when they've gone through hydrogen to helium fusion and fusion from helium into carbon and oxygen in their cores. Right? Low-mass stars, up to a few times the mass of our sun, will die this way. And the core, remember, the outer layers get puffed off into space as a planetary nebula. The core collapses down till it's about the size of the Earth, an incredibly dense state that we call a white dwarf. Now, the force that prevents a white dwarf from collapsing any further is something called the degeneracy pressure. The electron degeneracy pressure, the fact that the electrons don't want to get any closer together, right? Electrons are snobbish, they hate each other, they just don't want to be in each other's space, okay? You're like, get out of my face, dude, I need my space, okay? But the snobbishness of the electrons can only work up to a certain level. If that object, if that dying star is too heavy, then gravity will counteract the snobbishness of the electrons. This means that there is a maximum mass, there is a weight limit for a white dwarf. A white dwarf cannot be heavier than 1.4 times the mass of our sun. Again, that means that only low-mass stars can die as a white dwarf unless they go on a really serious diet before they die. All right? They can lose a lot of mass in one of those planetary nebulas, puffing the gas into space, but they can't lose all of it. So not all stars will die as a white dwarf. Now, because a white dwarf has a specific mass limit, life gets very complicated for them when they live in a binary star system. Binary star system is two stars orbiting around each other under the force of gravity. And for most of the stars' lives, they don't get in each other's space. They just orbit around each other. But remember that when a star dies, it expands out to become a red giant, or if it's large enough, a red supergiant. So let's take a binary star system where one of the stars has died first to become a white dwarf. And then the other star has now begun to die. And as the other star begins to die and it swells up into a red giant, you can see how the outer layers of that star are getting dangerously close to the white dwarf. And the gravity of the white dwarf, remember it's small in size, but it's still the mass of the sun. The gravity will pull in the material from this red giant. And that material spirals around and then sort of tries to go down and accrete onto the white dwarf, making the white dwarf bigger and heavier. So we call this an accretion disk. The material, it's like water spiraling down a drain, but here it's going down a gravity drain, spiraling down to the white dwarf. Well, the white dwarf is in a really bad situation because remember that by the laws of physics, it's holding itself up by the snobbishness of its electrons. If it gets too heavy, gravity will win. White dwarfs don't want to get any heavier, okay? So what happens is, as this material is spiraling down into the white dwarf, what happens is the friction, if you rub your hands together, you can feel your hands getting warm. The friction from this material actually gets hot enough so that fusion can occur. And we can actually have an explosion, not of the white dwarf, but of the material in the accretion disk. So every once in a while, this material blows off explosively into space. And if you're watching it here on Earth, you're like, whoa, what just happened there? This system becomes 100,000 times brighter than average. And then it quiets down again, more material accumulates, and then boom, again. This is what's called a nova. Again, for historical reasons, the name is really confusing because the word nova means new in Latin, and this is not a new star. On the contrary, it's a dead old star, desperately trying to live out the rest of its retirement peacefully here. But they called them a nova because they would see the star in the sky where there hadn't been one. So to them, it was new. Okay? So this situation can keep going on and on and on and on and on unless too much material starts accumulating too fast and the white dwarf can't get rid of it fast enough. If that happens, the white dwarf goes over that mass limit, something called the Chandrasekhar limit, named after the scientist who figured this out. And if a white dwarf goes over that 1.4 solar masses, the white dwarf itself will explode in a kind of supernova. So there are two kinds of supernovas. One is a red giant or supergiant that explodes when the core becomes iron. That's called a type 2 supernova. A type 1, technically a type 1a supernova, is an exploding white dwarf in a binary system where the companion tried to force feed it a little too quickly.